What if I told you that the famous Pythagorean theorem is actually just a special case of a far more powerful and largely unknown geometric law? We all know the Pythagorean theorem is all about right-angled triangles. Now, let's duplicate this triangle and rotate the new one by 180 degrees. If we slide it so the two hypotenuses perfectly overlap, what do we get? A rectangle. We know that in a rectangle, the opposite sides are equal, and both diagonals are exactly the same length. Now, according to the Pythagorean theorem, we know that a squared plus b squared equals c squared. But look closely at our rectangle. We can actually rewrite this equation using the sides and diagonals of the shape we just built. We can think of a squared as the product of the two opposite vertical sides. We can think of b squared as the product of the two opposite horizontal sides. And c squared? That is the product of the two diagonals. So, if we read the equation purely based on this rectangle, it says, product of opposite sides A plus product of opposite sides B equals the product of the diagonal C. And guys, that is exactly what Ptolemy's theorem is. But it says this equation will not only hold good for a right-angled triangle or a rectangle. It holds true for other angles too, if a special criterion is met. Notice how all four corners of our rectangle sit perfectly on the edge of this circle. Let's do one thing. Let's start moving these points along the circle's edge and see if our equation still holds up. Look at that! As we move the points, the lengths of the sides change, the diagonals change, and it is definitely no longer a rectangle. But as long as those four points stay locked onto the circle, the math doesn't break. The sum of the products of the opposite sides will always equal the product of the two diagonals. This special shape is called a cyclic quadrilateral. But in math, we don't just take things on faith. We have to prove it. And to do that, we are going to use a clever little trick and find some hidden triangles. Here is our cyclic quadrilateral ABCD. Watch closely as we draw one new line to crack this whole thing open. We draw a line from B to a point K on the diagonal AC. But we don't just place K anywhere. We place it so that this angle here, ABK, is exactly equal to this angle over here, DBC. Now, consider triangle ABK and triangle DBC. The angle CAB and angle CDB subtend the same arc CB, so they are equal. So, by the AA criteria, these two triangles are similar. From the similarity of these triangles, we can write the following proportion, AB over DB equals AK over DC equals BK over BC. From this, we can derive that AB times DC equals DB times AK. Now, consider triangle KBC and triangle ABD. The angle ADB and angle ACB subtend the same arc AB, so they are equal. Now, angle ABK and angle DBC are equal because of our construction. If we add angle KBD on both sides, now we have two pairs of equal angles, angle ABD equals angle KBC, and angle ADB equals angle KCB. Therefore, triangle ABD is similar to triangle KBC. From this similarity, we get the proportion AD over KC equals BD over BC equals AB over KB. In particular, AD times BC equals BD times KC. Recall from our first similarity that we had AB times DC equals DB times AK. Adding these two equations, we get AB times DC plus AD times BC equals DB times the quantity AK plus KC. But AK plus KC is just the diagonal AC. So we have AB times DC plus AD times BC equals DB times AC. And that, my friends, is Ptolemy's theorem. In a cyclic quadrilateral, the sum of the products of the two pairs of opposite sides equals the product of the diagonals. If you like this video, please subscribe.